Hello everyone. So in this lecture we are going to talk about how to delete a node in the binary search tree. So already we have seen that how to search a node, how to insert a node, and now the next operation is how to delete a node in a binary search tree. So we have seen that inserting and searching any node or any key value in the binary search tree is a very straightforward procedure. The deletion operation is little tricky, or you can say little complex, and we will see that how it can be done, because there may be many cases arises. You may want to delete a node which is existing as a leaf, or you want to delete any node which is uh, existing as an internal node. So when I say internal node, then internal node may have one child, may have two child, or you may have any left subtree or right subtree associated with that node. So first we will discuss its algorithm. We will discuss different cases that are applicable in the node deletion, and then we will take one example to realize that how these algorithms work in the real binary search tree. So in the binary search tree we have three scenarios, or you can say three cases of deletion. So case 1 and case 2 is a very straightforward procedure to delete a node, but in the case 3 we need to do some more exercise in order to delete the desired node. Now the case 1 says deleting a node that has no child. So if you want to delete a node which is actually a leaf, then it's a straightforward procedure. You need to search the node which you want to delete and then simply delete it. So this is an example. Here this is our binary search tree is given to us, and we are interested to delete the nodes with the value 78. So keep in mind, whenever we work with the binary search tree, we are always provided with the root address. So we start with the root address and we will search 78. So here we will check, is this null? Now when we say that tree equals to null, that means tree does not hold any address of any node, and it is assumed that tree is empty, and we can say that the deletion is not possible because the tree is empty. But if the tree is not null, that means that there exists a tree. Maybe the value which you are looking may not exist in the tree, but the tree exists. So because this is not null, because we have an address of this node, so we need to search that the element which we wish to delete is more than this or less than this or equal to this. So we will compare the value which is stored at the root. So this is 45 and we are looking for 78, and 78 is more than this 45, and we know that the more values or the larger values are existing at the right subtree. So it will pass the address of the right subtree. Now we are here, and then again we will compare that the value stored here is 78 or less than 78 or more than 78. So we will find that the value stored here is less than 78. That means it will move to the right subtree. Now you are here, and then again you will check that what is the status, and you will find that this is a node you want to delete. So this is shown here. So we start from here, and then we move to this node, and then we move to this node, and we have realized that this node is a node that we want to delete, and we simply delete the node, and this is our final tree status. Now this node is being deleted. So when you want to delete any node which has no child, you can simply delete it, or you can say deletion of a leaf is a very straightforward process. You can simply go to that leaf and remove that leaf from the tree. Now move to the case 2. Now deleting a node with one child. Now this is not a leaf, this is an internal node which has only one child. So what is required in this case? Node child is set as a child of the node parent. So if you want to, now this is a scenario, this is a node you want to delete, so you need to make this node as a child of this node. This is required. Or if the scenario is something like this is a node you want to delete, so you need to make this node as a child of this node. Okay, so the very first thing is we need to reach to the desired node, and then we have to check that it has one child or no child. If it has one child, then we will do this procedure. So if the node which we wish to delete has a right child, or you can say if the node that you wish to release is a left child of its parent, then its child, whatever the child it's having, it's become the left child of its parent. Now let me repeat again. This is a node to be deleted, and this is the right child of the parent. That means any of the child after deletion will become the right child of its grandparent. Okay, so let us see this scenario here in an example. Okay, now here we are interested to delete a node with value 54. So this is the scenario. Again, we have to start from the root node, and we will see, is this 54? No, 54 is more than this. We will go to the right subtree. Is this 54? 54 is less than this. We go to the left subtree. And this is the node that we are looking for. Or you can see one by one. So this is where we started. Let me clean this part. We started from here. And then because 54 is more than this, so we reached here. So you can see here we reached here, and then 54 is less than this, so we reach here. Okay, so now this is the node that need to be deleted, but this node is not a leaf node. It has a child. It has one child. So what is required? We need to delete this node, and this node is going to become a left child of this 56. So you can see here that this node is deleted and 55 has been attached here. So what we are doing here is we are simply looking for the logic. So far we have seen with the cases of leaf, and now with the cases of node with one child, and then we will move to the other case where we have a node with two child. So first we are focusing on to understand the logic. So once we understand the logic, then you will see that how we can write a proper algorithm for it, so that we can able to implement this logic in any program, or you can say as a program we can implement it. So case 3 is deleting a node with two child. So here we have third scenario where we are looking for deleting a node which consists of two child. Now here we need to find out the in order predecessor. Now one thing to keep in mind, now here we have two choices. You need to finalize, or you need to decide that which of the two procedures you are actually using in your algorithm. So one is in order predecessor is basically the largest value in the left subtree, or the in order successor, that means the smallest value in the right subtree. So now let us understand what is the meaning of in order predecessor. So in order predecessor means the exactly previous value than this. When I say in order successor, it means immediately next value after this. So how can we find out? So in the left subtree, if you find the largest value is the in order predecessor, and in the right subtree, the smallest value is the in order successor. So you need to take any of the cases. So if we are going with the in order predecessor, then we need to find the largest value from the left subtree, and that value we need to replace. So if we are going with the previous value in the left subtree, we find the largest value and then replace the value with this node. This is required in this method. Okay, so let us take this example. Here we want to delete a node with value 56. So we'll start from here. We are provided with this node address. This is the root address, and then 56 is more than this, so we will move to the right subtree. Now this is the scenario where this node to be deleted, and it has two child. It has left child as well as right child. Now let's say we are working with in order predecessor, and then we need to find out the largest value. So what we will do, when this node is find out to be deleted, we will look for the in order predecessor. So from the left subtree we will find the largest value. The largest value is this one, and then we will replace this value from this node. So you can see here this is replaced here with 55, right? Now we will move to the left subtree, and now our question has been changed. Now our objective is not to delete 56, but now we will try to delete 55. Means whatever the value you are replacing, now this need to be deleted. So now onwards you have started with a new problem and you keep on searching 55, and whenever you get 55 you need to delete it. Now in the third case, what is actually happening, you are converting the case number 3 to case number 1. So first you find this largest value, you replace it, and now your new problem started and you are trying to delete 55, and when you search in the tree you will find that this 55 is existing as a leaf that you can easily delete. So this is what you are getting. And now in this tree is still a binary search tree and your 56 value is deleted. Now this is the logic that we have understood so far, that we can come across whenever we need to delete any node in the binary search tree. Let us give a formal structure in the form of algorithm. Whatever the three cases we have discussed, let us look in the form of algorithm. This is the algorithm for deletion. So the name of algorithm is given as delete. Here we have to pass the root value and the value which you want to delete. If the tree equals to null, means the address which you are passing is containing null value, that means it is not being found. Now keep in mind, this scenario may be occurring in two situation. Initially when you start your algorithm and at the very first stage you find tree equals to null, that means the tree does not exist. The tree does not exist, and you can say that it's not possible to find. Or you may also find this null when you are keep on traversing from node to node and you realize that the value which you are searching is not existing. Okay, so if the very first time tree equals to null, that means the tree does not exist. Tree does not exist means definitely if there is no tree existing, the value which you are searching will not exist. Or otherwise, if it is not the very first stage, that means you have keep on searching and you are not able to find the node, that means that particular value is not existing. Okay, so if tree equals to null, then the value is not found in the tree. Else if otherwise, mean the tree is existing and you are trying to search that value. If the value which you want delete, if the value in the node which you want delete is less than the tree data, then you have to search in the left subtree. So already we are aware or we are familiar with this kind of statement. Tree left means we are actually moving to the left subtree. We are traversing the left subtree. So we have scenario. If the tree is null, value is not found. If the value you are searching, we have to go to left subtree. If the value is more than the root, then we need to go to right subtree. So either the value is less or more or equal. So whenever any value is given to you, either it may be less than or equal to or more than. So we have checked the less case. If the value is less, we go to the left subtree. If the value is more, go to right subtree. And this is the case when value is equal. Now when value equal means we are able to find out the node which is to be deleted. Now we have three cases. The case number one is it's a leaf node. Case number two is it has only one child. Case number three is it has two child. Now if tree left and tree right means the left child exists, means this is true, this is not equal to null, and this is also not equal to null. Okay, this statement means this is true, it means both child exit, that means this is case 3. We are talking about case 3. So what is required? Then set temp find the largest node from the left subtree. This is from the left subtree. We are trying to find out the in order predecessor. In order predecessor means we are trying to find out the largest value from the left subtree. We have find out and return to this variable temp, and this node value, first we have to find out that node which is existing as the largest value, and this node value we have assigned to this tree data. Means it is a scenario, this is the node which you want to delete, so you need to find out which is the largest value. So definitely this is the largest value, and then you have to assign this value to this node. This is what we are doing here. And then delete tree left temp data. Now as I told you, in the case 3 we are actually converting this case 3 to case 1. In the case 1, what is happening? Now we are not actually looking to delete our desired value, but now we are looking to delete this new value. So in the case 3 we have changed the scenario. We have replaced this value with the value which we want to delete, and then we are looking for this node to be deleted. So now onwards we start from this tree and we search for this node to be deleted. So here you can see delete tree left, and in the left subtree we are searching for this value to be deleted. We are searching for this node who has this value. Okay, now this is your case number 3. Now then we have two more possibilities are also there. What is that? Else set temp equals to 3 means the node does not have two child. Else means you are only coming here when this condition is not true. Okay, so the node does not have two child, then what you will do, you will take one variable and assign the address of the node to this variable temp, right? Now this tree represent the address of the node that to be deleted, right? If tree left equals to null and tree right equals to null, that means this is case 1. That means you have reached to the node which is to be deleted who does not have a left child and does not have a right child. In that case, what you will do, you will set tree equals to null. So what is the scenario? The scenario is this. This is a node. Let's say this is a node that need to be deleted, right? And you keep on moving from the root, and you keep on moving from top to down in search of the node to delete it, and you have reached here. Okay, and you are calling it as a tree. Okay, and then you have also find out that it has no left child, it has no right child. So what you did here, you first assign this address to temp, and then what you did, when you find that it has no left child and right child, you did set tree equals to null. That means you simply made this as a null. That means there is no link for from this node, and now this is deleted actually. And then you will set free this temp. Okay, so set tree equals to null. Now, so we have seen the case number 3 when the node has two child. We have seen the case number 1 when the node has no child. Now we have left with case number 2 where the node which we won't delete can have one child. Okay, so let us look here. Okay, else if. Now keep in mind this is or else if cases means in all of the in all of the situation you only one can execute. Okay, because this is or else part, either this, all this, all this, all this, all this. Okay, so if none of this matching, then you are going here else if tree left is not equals to null. So far we have seen that this is a scenario when it has two child, and this is a scenario where there is no two child, right? That means now only one possibility is remaining, that it has one child. Now we have to check this child is a left child or right child. Okay, so this is case number 2. So if tree left is not equal to null, this is the scenario when it says that it has left child. It has left child. So what is required? Set tree equals to tree left. What does it mean? It means you may, now let's say this is a node. You can think like this. This is some tree. It is a part of the tree, and this is a node to be deleted. This is a node to be deleted, and it has a left child. There is no right child existing, but it is a left child. So far you are pointing here, means tree is pointing here. Tree is referring to the node which is need to be deleted. Okay, so what is required here? So far we took one temp variable which actually assigned this tree address. That means this is also pointing to this node, right? If the tree left is not equal to null, that means its left child exists. So we want to delete this node. Set tree equals to tree left. Now, so tree is actually pointing to this node, and we are saying that now tree must point to tree left. So instead of pointing this, it will point to this. Okay, so set tree equals to tree left. So means tree is pointing here, this node, now it will not point to this, it will point to this. Now otherwise, if this is not the left child, then else part, again we are in the else part. Set tree equals to, now else means already we have identified that this is case 2. Case 2 means it can have one child, so either it has a left child or right child. So if this is, if this is true, that means it has a left child. If this is not true, then definitely it has a right child, because we have only two possibilities, either left child or right child. So this is a scenario. Let's say this is a scenario where this is the node to be deleted, and this is pointed to by the tree, and this is the right child. And what is required here, if this is the right child of the node to be deleted, set tree equals to tree right. That means now we want to point this to this, okay, and then free temp, and temp is actually pointing to this node, so we will just free this, and now from here actually we are able to point to this node, and this is actually deleted. So when we lose the link of this node, it actually means that we have deleted from the tree. So here also we have lost the link of this, because now tree is pointing me from here, we are able to point to this node, and this link is lost. That means we have removed it. And also we are freeing this memory by using this free temp, or so that this memory area can be available for other applications to use. So we have seen that all the cases that how this algorithm can be implemented using any programming language. This is the logic. Now we will take one example, and we will realize that how the things can be done. So this is the algorithm that we have just discussed about the delete operation, and I think now you understood that this refers to your case. Just a minute, let me check. This is your case 3. This is your case 1, and this is all about case 2. Now let us take an example. Let's say I want to delete node with value 40. So how this can be done? We have to start from the root node, and then the value which we are looking is 40, so we will go to the right. Now the 40 is less than this 45, so we'll go here, and we reach to here 40, right? And this is the case where we don't have any child. So I believe that you understood this algorithm, or we can also go with the step by step that how the things are working. So when we want to delete 40, so the tree is not null, because the tree is having the address of this node. This is not null, this will not execute. And then we will check if the value which you want to delete is less than the tree data. So no, this will not execute. Value is more than tree data, yes, then we will pass the uh, tree right. That means now we have passed this, and we have to work on this. It will make a recursive call. Now these are the recursive call. And then again, now you are here again, you have passed the address of this node, and we are searching for value 40. Now again, this is not null, this will not work, and it will check that the value which you are looking is less than this. So in this case, this is true, and it will pass the left subtree. So you are here now. So again, you are calling recursively, so the tree is not null, so this will not work, and the value which you want delete is not less than, not more than. So you escape both this part, and you are here, and you will see that the tree left and right will exist. No, this will not exist, because it does not have any child. Then you go here, and you see if the tree left is null and tree right is null, that means this is the tree which is representing this node, and it has no right, it has no left. That means this condition is actually satisfied. Then what is required? Set tree equals to null. Simply keep this as a null, means set here as a null, and that's all, and you are able to delete this node. Now we will take another scenario where it has one child or two child. So we'll take one by one both the cases. So let us take another example where the node is having a one child. So let's say this is the case. I want to delete 21. So we will do it quickly because I believe that now we have understood that how the things are working. So to delete 21, we start from here. 21 is less than this, so it will go to left subtree. 21 is less than this, it go to left subtree. 21 is more than this, we go to right subtree. And here you reach to the scenario, and it will keep on checking all this. And actually, this is the node which has one child. So when you reach here, uh, this is actually tree. Tree is a pointer, you can say. It points to this node, and we have assigned this address to temp. So actually what we did tree equals to temp, means temp is also pointing to this, right? And then what is required, it has a left child. So what we are doing, we assign the address to this tree. So we said that tree equals to a tree left. So tree left means this node address, and we assign this to this. Okay, and that means from here we are now able to connect to this, right? And we set uh, free temp, means temp is pointing to this node, and this is going to be set free, and we are able to delete this node. So we are 19 will be actually replaced, you can say here. Okay, the next part we can take to delete any node which consists of two child. So let us take one node, let's say 45. We want to delete 45. So what is required, again we start from here, and we will check that this value to delete it is more than this. Yes, we reach here. Now 45 is the node that we have reached, and we want delete. Now uh, what is required, whenever we want delete a node which has two child, then we will be finding a uh, in order predecessor or in order successor. Okay, so let us take, we are doing the in order predecessor. So in that case, what we will do, we will look to the left subtree and find the largest value in the left subtree. So this is the only value. Now this we are going to replace here. So this become 40, and then we will in the left subtree we will start searching 40 to be deleted. And because this is the only node here, we immediately reach here and we remove this, and this is how we can delete 45. 45 is now deleted. Let us take one more example. Let us take one example to delete 18. So we start from here. 18 is less, we move here, we move here, and now this is the node to be deleted. So what we will do, either we take in order predecessor or the in order successor. So I will do it with both the cases. I will take in order predecessor first, means from the left subtree I need to find the largest value. So I will find this is 10, and I will replace this. So I will be going to write 10 here. And now in the left subtree I will search value 10 to be deleted. So we know that now this is the tree given to us, and it's very easy. You can start from here, reach to the 10, and 10 is a leaf node. Simply delete this, and now this is our answer. So we have this tree, this 18 is deleted. So actually to delete this internal node, now one thing to keep in mind, we never delete any internal node, but logically we have deleted it. So if you look at this, we need to delete this node. So uh, actually this node is not deleted, but logically the impact of our operation reflects that this is deleted, because the value which is stored here is being replaced by some other value. So now this node is containing 10 instead of 18, and now there is no 18 existing. So you can say that 18 is deleted. Let us take one more example. Let us take the example of 18 again, and in that case we will be using the in order successor. So again we start from here, we move to the left, we are here, and now we will going to take the in order successor. That means from the right subtree we take the smallest value, and the smallest value will always be the leftmost, you can say the child. So you can reach here, this is the smallest value, you are going to replace this here, this becomes 19, and you move to the right subtree and look for the 19 to be deleted. So you keep on searching. Now this is your tree, and you will reach here and delete this node, because this is the leaf node. We'll take the last example where we want to delete a node which is not existing here. So let's say I take 90. So we start from here. 90 is more than this, go to right. More than this, go to the right. More than this, go to the right. More than this, go to the right. Now here, more than this, go to the right, and the right is actually null. Right is null. So when your tree is getting this value null, and when it is and again when it's called recursively, so you are reaching to this case, this scenario, tree equals to null, and you say value is not found in the tree, and it will return that value not found, and actually 90 is not existing in the tree. So now I believe that you have understood completely that how the deletion can be done or applied in the binary search tree. We have discussed thoroughly all the cases, case 1, case 2, and case 3. Okay, this is all for this lecture. Thank you very much, and see you in the next lecture. Take care.